All right, so today I want to finish linearizing. Why do we care so much about linearizing things? Why is that such a big deal?
Because we're in operations.
See, if you had said we were in linear programming, you would have been fine. So close. Right? This is why we care so much about linearizing. We have a procedure, we have a black box to solve linear programming problems. Now, unfortunately, if we do binary or integer linear programming problems, the method is no longer going to work. And in fact, we do not have a really good method to solve general integer programming problems. But we at least have a framework to attack them, and we at least have a framework to get something close. Do you remember the duality theorem? That if we looked at the dual problem, we could get an upper bound, a lower bound, we could get some idea of how close we were to the extreme value. Does that still hold if we have ourselves restricted to integer solutions? Did we need to use anywhere in the argument that our solution, our feasible solution, our optimal solution, had to be real valued, had to be integer valued? No. That bound still transmits over. So even if we can't solve integer programming problems exactly, we can often get a sense of how close we are. And frequently, we will be damn close. Okay, and you can quantify exactly how much that is. So if you want to see I'm within, say, 1%, frequently that's not so hard to do. How many of you are familiar with the Netflix challenge? Okay. How many of you are familiar with Netflix? How many of you are familiar with challenges? Okay, so the Netflix challenge was designed a couple of years ago to spur some basically very cheap labor for Netflix. This may be different than how Netflix would bill it. But their idea was to get people all over the world interested in improving their services. And they would give a big prize to the winning team. And then this might actually be a lot cheaper than R&D. It would also increase demand maybe. It would give good publicity to the company. And so the goal was to come up with a better algorithm than Netflix was using to improve recommendations of movies. So now whenever you go to almost anything, oh, you might also like the following, right? You get this all the time. Facebook does this in terms of which news stories they show you. Amazon does this in terms of what other products they show you. And the Netflix challenge was to move it up by about 10%. And it turns out this was a really good number to keep things interesting. A lot of groups very quickly got around 8 or 9% without too much trouble. But that last little extra bit was extremely difficult. And so this is sadly the way things are frequently in linear programming, is we can often get fairly close without too much work. But to get to the exact optimal is often exceedingly difficult. Yes?
Moving up what, 10%?
Oh, how well, and I'll just use it in quotes like that to cover me, you do at predicting whether or not somebody else would like this new suggestion. So based on your preferences, I will recommend this movie to you. So is it in Netflix's interest to have you get good referrals for future movies? Why?
You'll watch more and stuff on other sites.
But I mean, if you're paying for a monthly membership, does it really matter how much you watch?
Yeah, because it matters how many months you stay in.
It matters how many months you stay in. What else could matter?
Referring your friends.
Referring your friends. Right? So there's a huge incentive for companies to do a good job. For Amazon, it's a lot clearer why Amazon wants to recommend things for you to buy. And actually, yesterday was one of the few times Amazon's recommendations actually helped me. The first ones was, no, this book is extremely expensive, I'm not going to buy this. Hey, yes, that one is actually closely related to what I want. I'm looking to buy 4, 5, 6 Putnam books to help prepare for the Putnam. Yes, this one is a good fit. And so this was one of the times when Amazon was able to correctly identify what I was looking for. All right, so this is the general framework. If we can linearize things, we can use the methods we already know. So we went through a lot. I think we stopped at the exclusive, inclusive, or, and then we did the if-then statement. Did we stop with if-then? All right, so I want to do, we did half of if-then. All right, I'll leave the other half then as an exercise, and I'll move on. And we will do truncation. Okay. Just seeing who's paying attention. All right, so for truncation, we want y equals x if x is greater than or equal to x naught, otherwise 0. Okay, so we didn't do truncation last time? Okay, so think of this going back to our movie theater example. If the number of people who want to see a movie is greater than the capacity, we need to truncate it. We cannot sell more tickets, again, for the movies than we have seats. So again, this way might be going the wrong direction. If we want to truncate it the other way, that's not a big deal. I'm going to assume that if I'm above a certain threshold, I want to keep it. And if I'm below that threshold, I'm going to just set it to 0. Okay? Another way of looking at this is if you're not above a certain ante, it doesn't happen. There's a certain critical threshold to be a player and to come in. And if you're not at that level, no one's going to care. All right, so here are the different conditions that will do this. So we'll take z to be in 0, 1, as always. If x is less than x naught, then z equals 0. If x is greater than x naught minus delta over 2, then z equals 1. And then we're going to add these new constraints. Y minus x plus n sub x 1 minus z must be greater than or equal to 0. Y minus nx, y minus nz, nx times z, is less than or equal to 0, and 0 less than or equal to y less than or equal to x. Okay. Do we know how to do if-thens? Yeah, we did them last time. So we can now just use the if-then. You can see that this is very similar to working in a programming environment. The idea is you want to build up modules, you want to build up functions, you want to build up commands that you can just use. And you don't want to have to go all the way back to the basics. Who are my computer scientists? Have you programmed in machine language? Did you enjoy it? No, I mean, for a small amount of time, it's kind of fun to do, but you would not want to do a serious assignment in machine language, correct?
Correct, yeah.
A small thing, it's kind of fun to see that you can do it. A large, extensive thing, you want to write a Monopoly game program, you don't want to do that in machine language. It's the same thing here. For those of you who have sadly not gone deep in computer science, how many of you have taken calculus? This is supposed to be like, who's awake right now? Right? How many of you have ever taken the derivative of this function? Let's see if this derivative is working. It's partially working. Installment plan. F of z, sorry, I was doing complex a moment ago. F of x is 1701 x to the 1789 minus 123 x to the 124 plus 665 x to the 667. Have any of you ever taken the derivative of this function before? Okay. So everybody remember the definition of the derivative? Anybody want to use that? No. What you do is you isolate out laws of differentiation. You isolate out things like the sum rule, the product rule, the constant rule, the power rule. And in using those pieces, you can now take the derivative of a function like that. It's the same thing over here. In terms of how we're doing this, once we have the language of if-then, we can use that in advance. This is now something that's been modularized. And this is a great concept. This is a great way of looking at things. You don't want to keep going back to the basics. So whenever you're coding things, you want to work in an environment that allows you to just program the if-thens. You don't want to write the code directly for each if-then. We could do that and unwind that, and if we were trying to figure out the cost of this, we would do that. But you want to be able to just use a high-level language like this. This is one of the reasons I like Mathematica. It's not nearly as fast as a lot of other programming environments, but it's very user-friendly in terms of the command structure and how things are programmed. All right, let's look at what's going on. Z is 0, 1. If x is less than x naught, then z equals 0. If x is greater than x naught minus delta over 2, then z equals 1. And remember, we're assuming things are discretized. We're assuming each unit is delta is the smallest possible change. So if x is greater than x naught minus delta halves, then x is greater than or equal to x naught. So this will give us z equals 1 if y is greater than or equal to x naught, and it will give us z equals 0 otherwise. So all we have to do is now go from this value of z to a value of y. And that's all we're doing here. So now let's look at this equation. Let's imagine x is greater than x naught. So we'll assume right now x is greater than or equal to x naught. So that tells us z has to be, what does z have to be? 1. So now z equals 1. This expression has to be greater than or equal to 0. So what do we know about y? So since z equals 1 and this whole expression is greater than or equal to 0, what do we know about y? It's greater than or equal to x. Now if we look at this equation, this makes y at most x. And in this equation, well, when z equals 1, we have an nx over here, so this is no problem. Because y is at most x, this will be satisfied. So everything is okay, and when z equals 1, we get what we want. When z equals 0, it's going to be very similar. So case 2, we'll now have x is less than x naught, and so in this case, what does z equal? So z now equals 0, and so now in this case, if z equals 0, we get y minus nx plus nx is greater than or equal to 0. Well, nx is greater than negative x. In fact, nx minus x is still going to be positive. So over here, y is going to be, as long as y is not negative, huge negative number, we're fine. And in fact, this condition over here is going to prevent y from being a huge negative number. Y can't be smaller than 0. So over here, this equation and this equation, they both tell us y is not negative. Well, that's great, but we want y to be 0. So now we look at this equation. Because z equals 0, we have y is less than or equal to 0, and y is greater than or equal to 0. There is only one number greater than or equal to 0 and less than or equal to 0. And so we get y has to be 0 as well. So this gives us truncation. So we can truncate now without any trouble. Okay? So again, this is very useful for situations such as the demand for a movie theater. All right, so we have 2 more left. We have maxima and minima, and then we have absolute values. Okay, so now I think truncation was 5. See if the camera's... Yes?
For the truncation in the second condition.
Yes?
Sorry, the third condition.
Yes?
Why did you do greater than x naught minus delta when you said it's greater?
Just being safe. You could almost surely do x greater than or equal to x naught. Just trying to be really safe and just getting into good habits of how things could come out.
Are you allowed to do delta over 2?
Yeah. I can put in whatever constants I want. Nothing is ever going to take on the value delta over 2. The main thing for something like this is this way I don't have to use the equal sign. I can get away without using the equal sign and using strictly greater than sign. And so just maybe on a machine I might want to use a greater than rather than a greater than or equal to. Just have a little bit more of a separation.
I mean, the thing is you have like 3 other greater than or equal to signs.
Right. Although I know a lot of the equal signs will not happen because I have the nx's chosen to be very large. And so, again, this is where if you actually get to a programming point and try to implement this, some of these choices could affect how quickly things run. And these are outstanding things to think about and to investigate. Right now, I'm a theoretical mathematician at heart, and just, I know something like this keeps me safe. But in terms of actually going into the field, you would want to see, do slight tweaks make a difference? Have we done telescoping sums in this class? I think we did in the beginning of the year. And that how you do the algebra makes a huge difference in the runtime. So depending on how you phrase some of these constraints, you can code the same thing multiple ways, and that can have an effect in the runtime. All right, so let's do max min, or min and max. So on the minimum side, I will have y less than or equal to a, y less than or equal to b, y equals a, or y equals b. On the maximum side, I'll have y greater than or equal to a, y greater than or equal to b, and y equals a or b. Now, because I'm using ORs, we should ask, are we doing the inclusive OR or the exclusive OR, or does it matter? So does it matter if we do the inclusive OR or the exclusive OR? Yes?
No, because y can't be both.
I'm sorry?
No, because y can't be both.
It can't be both. So you'll pass the class and you'll pass the class. No, okay, okay. Only one person in this class can pass. Okay, I will remember this. So is it possible for y to be both a and b?
Yes.
Yeah. But if y is both a or b, y is also equal to a. So it's also equal to one of them in that case. So whenever you have situations like this, it's good to just tell a story. I like to tell stories in terms of passing and failing students. I'm a professor. It's what I have the most experience with. More on the passing side than the failing side. I'd like that tradition to continue. So over here, does it really matter if I use inclusive or exclusive? No. You can use either one. Use either inclusive or exclusive. Now, is this or here inclusive or exclusive? In the statement, inclusive or exclusive?
Exclusive.
That's an exclusive or in the statement on using the inclusive or the exclusive or. Why does this work? Well, y less than or equal to a. Do we know how to check something like this? Y less than b, we're just comparing things. Y is some expression involving our quantities. Maybe it's 14x132 plus 12x389. We just have some expression for y. Is it less than or equal to a? Is it less than or equal to b? And so let's say those two values are attained. Then we want y to be equal to a or b. And what's the only way that that can happen? What is that going to force y to take on? The smaller value. Let's say a for definiteness is 80 and b for definiteness is 100. If I take y to be 50, well, it's not equal to either a or b, so that would be false. So y has to either be 80 or 100. And because it has to be less than or equal to a and it has to be less than or equal to b, the only way that can happen is if y takes on the value of 80. I'm not going to go through the proof for maxima. It's very similar. The whole point of this is that we have minima and maxima that can be done within the language of linear programming. We can introduce more constraints. All right, the last one is absolute values. This is the one that should be the most fun. And why should absolute values be fun? Does the absolute value function look linear? No. Right, so 7. Absolute. It looks mostly linear, but it does have that really bad point. All right, so let's do it this way. So we'll do a less than or equal to x, 2 negative a less than or equal to x, and then 3 x less than or equal to a, or x less than or equal to minus a. And again, we have an or, inclusive, exclusive, or does it matter? Well, let's think. Let's say a is 50. So if a equals 50, what do we have? We have 50 is less than or equal to x, negative 50 is less than or equal to x.
Oh, it doesn't matter.
So then we get x is less than or equal to 50, or x is less than or equal to negative 50. So when we look at these conditions, the only one that really matters is the smaller one. If x is greater than or equal to negative 50, here it's the larger one that it's the larger one that matters. If x is greater than or equal to 50, it's got to be greater than or equal to negative 50. Right? So in these two conditions, if the first condition holds, does the second condition give us any information? No. Now we come down here, and now we say x is less than or equal to a, or x is less than or equal to b. Can both of these conditions hold? If it's 0.
If it's less than negative.
If x.
Less than or equal to negative 50.
So it's possible for both of these conditions to hold. But if I want these to hold, and these to hold, what's the only way all of these can hold? So over here, this tells me x has to be at least 50. Now if I come down over here, what's going to happen? If this is the condition that held, say x is negative 51, that's inconsistent with this up here. So the only way this can hold is if it's the x is less than or equal to 50 works. And that's going to give us the absolute value. What would be the one interesting value of a? 0. So 0 is less than or equal to x, negative 0 is less than or equal to x is greater than or equal to 0, x is less than or equal to 0, or x is less than or equal to negative 0. All right. Both of these conditions are the same, both of these conditions are the same, doesn't really matter. Do I need to consider the case where a is negative? Why don't I have to go through the argument when a is negative?
This might be a silly question, but we have 0, right? It's not like del over 2, like we actually have the 0.
Yes.
Okay.
Because we're assuming everything is an integer multiple of delta. So the possibilities are 0, delta over 2, 2 delta over, 0 plus or minus delta, plus or minus 2 delta, plus or minus 3 delta. Do I have to worry about doing the analysis when a is negative 50? No, why not?
It's the exact same except the order of
Yeah.
evaluates.
Just call a negative b. And you just change your letters. It's the same argument. I can do a change of name. So by symmetry, if I can handle the case when a is positive, I can handle the case when a is negative. Because a and negative a appear symmetrically in everything that happens. I can't tell the difference between them. So being able to note symmetry arguments often saves you from having to handle many different cases. All right, so this gives us the absolute value function. So the absolute value function is linear. Okay, and again, when I say the absolute value function is linear, I want to make sure this is not taken out of context. This does not mean you can now differentiate it. It means I can handle, or you can handle, the absolute value function within the confines of linear programming. More specifically, within the confines of integer linear programming. Because you need to introduce these additional things. We've got an OR statement here. I am not saying I can handle the linearization of the absolute value function without introducing binary integer variables. That would be a phenomenal achievement. We don't have that. Yes?
So when you start linking together all these different constraints, all these different visualization
Right.
techniques, you're obviously adding lots of new variables.
Oh, yes.
What does that do? Obviously, it makes the runtime worse.
Yeah. Yes. And so the more you do, the harder it becomes. And then the question becomes whether or not it's better to come up with a different technique that allows you to handle some of these constraints directly rather than going through integer programming. And then this is where I'm unfortunately not an expert. I don't know from a real world perspective what the cutoff is for the trade-off. You know, how much can you do with this before it just becomes so bad? Frequently, and the beginning of our textbook has a great example about this, where they talk about the oil company. How long did it take you to make up your money? I know oil companies have a lot of money, but they don't like just throwing it away. And the guy pauses and moves his hands and says, about a week. And then even if you can't solve the problems exactly, to just get closer, the scale involved is often so vast that these savings are enormous. And again, small mom and pop dime store, you're not going to see that. But you have something like Walmart. You have something that has this massive distribution network. A small increase in efficiency magnifies because of the volume being done. Okay, yes?
Is there a way to use the absolute values and maximum minimum in the linear program, the function we're trying to analyze, or optimum?
Yes, absolutely. So what we can do is we can take the objective function and we can replace terms in the objective function that involve the absolute value. And we can then add new variables, which then come into the constraint part. Absolutely. So for example, maybe we have a term that is the maximum of 3 and 18x. Is maybe you're capped at a certain amount, and you have a term like this coming in terms of your revenue stream. We can handle that. Absolute value. we can handle an absolute value in the objective function. Now, how many of you have seen the method of least squares? One of my favorite topics. That involves squaring. Is squaring linear? Damn it. All right. Well, we'll get back to that in a moment. Do you have a question?
Yeah, it seems like using this machinery, we could also approximate functions that have kind of like finite piecewise linear.
Mm-hmm.
And so if we had something, say, quadratic in our objective function, could we, by adding a whole lot of variables, get kind of like approximation of that quadratic term?
Yes. And the better approximation you have, the slower your program will be to run. And you'll have that horrible trade-off. One of my favorite quotes is, "What is amazing is not that the horse sings well, but that the horse sings at all." And the way you need to view this is you can at least get this into the framework where it can be done. And it can be automated. I'm trying to think. Who remembers their first computer? Picture your first computer. I will tell you the first computer that I can remember using. It was a Timex Sinclair 1000. You can Google this later and try to see exactly how old this machine is. To play Flight Simulator, which was basically a bunch of straight lines and circles, you would put a cassette tape in, and there was a cassette player that was connected to the computer. It would take about 7 minutes to load Flight Simulator. I liked to program, and my father was very generous, and he bought the memory expansion to get up to 16 kilobytes of memory. I was making a little game, and we actually ran out of memory to have the ship moving. Computers have advanced greatly. And so I don't have to be as clever programming. It mattered the order in which we erase things in terms of doing things because of the amount of time it took to actually display things on the screen. If your computer is sufficiently fast, you don't have to worry about being efficient. If you've never looked at the Project Euler problems, we're doing a little bit of that in Math317. These are great problems, which is a mix of math and CS trying to do things efficiently. For some things, the problem is so simple that even if you do these exchanges and put in these complications, it can still be done in such a small amount of time that it doesn't really matter. And if you're going from something that runs on the order of 1/10 of a second to on the order of 5 minutes, for a lot of things, 5 minutes is no problem. When it goes from 5 minutes to 5 days, that becomes a problem because then you have to wait quite a while before you can do your next run. All right. All right, so building on your question, quadratic functions are actually linear. And again, I do not mean a parabola is a straight line. I mean I can replace quadratic terms with linear terms. Lots of linear terms with lots of constraints. But I can at least get them in. Okay? So we'll assume only have binary variables. I'll leave the more general cases. An exercise, I just want to show you the power of linear programming, that we can handle quadratic terms linearly. Why might you want a quadratic term? Why might you want to take the product of two indicators? Why might we care about the product of two things? Yes?
Well, something like least squares, it helps because it punishes you the farther away you go.
Oh, so if we want to use least squares, we have squared terms in it. So there we've definitely got to do it. We'll be taking the product of something with itself. Okay, good. That's one example. Anybody ever do any predator-prey models? You know, rabbits and wolves.
Oh, yeah.
Do you want to be a rabbit or a wolf? When wolves are trying to eat rabbits, there's lots of ways to model it. You often have an interaction term, which is a product of the density of the wolves and the density of the rabbits. You know, the more rabbits there are, the easier it is for a wolf to find a rabbit and eat it. And the more wolves there are, the easier it is. And so it's not unreasonable to have a product term like this. If we go back to the movie theater setting, maybe you're worried about, am I showing an X-Men movie at the same time a new Spider-Man movie is being shown? And if that's happening, there could be a decrease in demand. So maybe I show my Spider-Man movie at time t, and it has a certain demand. And I show my X-Men movie at time t, and it has a certain demand. But then I have to subtract off maybe this d, sxt, xst, xxt. Because if I'm showing both movies, I've got some people, they'd love to see Spider-Man. They'd love to see X-Men. As long as there's some superhero fighting bad guys, they're happy. But they cannot see both movies at the same time. And so you can't double count them for demand. And so you would have to subtract off a term like this. So it's extremely important in a lot of these problems to have this interaction term. Okay? So hopefully this has motivated why we need to handle polynomials. And this is the last of the linearization part of the lecture. Okay? So we understand now why we need to handle something like this. The question is, how do we do it? So let's assume we have the following. X and y are in 0, 1, and we have this term x times y. And we want to understand this. Well, we can use all of that stuff we've just been doing. This is a great application of it. And I was trying to decide, do I want to make this a homework problem, or is this worth doing in class? And this is sufficiently important that I decided I wanted to do this in class and really go over how you would handle this. What can you tell me about x times y? I'm sorry? Okay. So x times y, when is it 1, when is it 0? Okay. Can you give me a nice way to phrase they're both 1? X equals y equals 1. Any other ways? And the product is 1. So you win the circle award of the day. And actually, if you look at these in the right way, they are circles. And so that is worth a circle. Okay, what's another way of looking at x times y equals 1? X plus y is greater than 2. Or we could actually just say x plus y equals 2, because they only take on the values 0 and 1. And otherwise, it's x plus y is less than or equal to 1. Does this look at all familiar? We've been talking about how to do stuff like this. So we could do this, we could do this as an if-then statement. We could do this as a truncation statement. If the value is at least 1.5, then our new variable is just going to be x plus y. If the value is less than 1.5, we truncate it to 0. And in fact, this is one of the reasons why I phrased truncation the way I did, because I had this application in mind. Okay? So we can do this, truncation. If x plus y is greater than or equal to 1.5, then we'll let z equal x plus y, the truncation, else z equals 0. And now we've replaced the product xy with z. What if we had more than 2 variables? Probably. And then, okay, right. So if we want x times y, we would replace x times y with z halves. So then replace xy with z divided by 2. And I will try to make the z and the 2 distinguishable. What if we had more than 2 terms? What if we had x times y times z?
You need to truncate and have the sum of all the variables be greater than or equal to how many variables?
Yeah, greater than or equal to 3. It actually becomes very easy. Is it difficult to add more variables? No. So once you have the truncation handles this extremely nicely. And you might think, oh, well, maybe if I have 4 variables, I split x and y together, and then z and w together, and I have those ones, then I maybe combine them together and have some kind of tree. Don't need to do any of that. The truncation handles this extremely nicely. Okay, So any questions on, yes?
What if we don't have binary variables?
Make them. So, that's a great thing to think about as to what would you do if your variables were not binary? Is there a way around this? And in all of these problems, it is not unreasonable to say, I will assume all my variables are in some bounded domain. I know they often tell you in college that your possibilities are limitless with a Williams degree or whatnot. I will throw cold water on that and say, no, I believe you are all extremely limited in terms of what you can do. For all practical purposes, I believe you can go out, succeed to great, great levels. But what is it? The 4 lines. Climb high, climb far. In the sky, your goal, the star. It's still stars a finite distance away. All right? You're not going to get up to infinity. Okay? Don't use mean words in public. All right, the knapsack problem. So we're going backwards a little bit, but now that we've got all this stuff on linear programming and linearization, it's good to see how close is linear programming to real programming. And again, you can do this stuff in either order. I decided I wanted to have the fun of going through, seeing what we could linearize, and then see, is this going to be sufficient? And the whole point of linearization is to try to convert things to a framework that we can attack. But sadly, it is not the case that a real solution is always going to be close to the integer solution. So here's one of the most famous examples. You have a knapsack that can take 100 kilograms. And you have 3 items. The first is, just want to make sure I get the numbers. I want to use the same ones as in the book. Okay, it's 51 kilograms. And $150 per unit. The second is 50 kilograms and $100 per unit. And the third is 50 kilograms and $99 per unit. All right. So we have our 3 products. And they are 51 kilograms, 50 kilograms, 50 kilograms, 150 per unit, 100 per unit, 99 per unit. And we have a knapsack that can take 100 kilograms. Do you want to be good or do you want to be evil? Evil. You're robbing the store. All right? You want to fill up your knapsack with as valuable merchandise as possible that you will then sell on the street. Okay? You're also really strong. You have all the equipment you need. You can smash units up. You don't have to take a whole unit. And you can sell fractions of a unit. Okay? So if you want, imagine maybe you have a valuable liquid or substance. And you're just choosing how much of it to pour. And 1 unit is 51 kilograms. But if you want to take pi units, you can do that. Without going through and writing the linear programming problem, can you tell me what you're not going to do? Yes?
Take nothing.
Okay. Yes, because we are evil, but yes.
Take the third.
Yeah, we're not going to take the third. We're smart enough not to go for the third unit. The third unit is dominated by the second unit. It's the same cost per unit, but it gives us less money. So it's all down to we want to take some amount of the first and some amount of the second. This is actually a Calc 1 problem. We take x units of one, we take y units of another. X plus y equals 100. We want to maximize 150x plus 100y. I claim we don't need to use calculus for this. What should we do?
You want to take the item that's densest in terms of value.
Right. So we want to look at which item is the best per kilogram, the best dollar per kilogram. And if you look at this, this is essentially $3 per kilogram. It's a tad less, but it's basically $3 per kilogram. This one is $2 per kilogram. So what you would do is you would just take, 100 over 51 units of this, and that would get you your revenue. All right, so is it clear what we should do? Okay, so if you ever find yourself in the situation where you need to ransack a store, you're now prepared. Okay. Unfortunately, this is no longer such a nice store where you have these continuous things you can steal. You now have TVs, VCRs, and whatnot. And if you take half a TV onto the street to try to sell, you're not going to get much for it. You've got to take the whole TV. Okay? Now, are we still in the situation where we would never take Unit 3? Yeah, Unit 3 is still dominated by Unit 2. We have to choose. And our knapsack can only take 100 kilograms. What do we do now? Yes? Take 2 twos. So in the real case, it's all Unit 1. And we get approximately how much? A little bit under 300. I don't know, I'll call it maybe like 294, something like that. I don't know exactly what it is, but it's a little bit less than 150. Ballpark, it's 294. In the integer case, all Unit 2, and we take 2 copies. And now what do we get? What's our revenue? 200. This is why the knapsack problem is such a great problem. Notice how much different the revenue is. And notice how different the solution is. Yes?
So, say like a company is doing something like this and they have that constraint, knapsack can only take 100 kilograms.
Right.
Is it like realistic for them to, are these problems too complicated where they would see that if they make their knapsack 2 kilograms like stronger?
Well, so one problem that you would want to have here is the expandable knapsack. And is it worth a little bit to me to buy a knapsack that's a little bit bigger or to have a little bit of an addendum? Absolutely. So you would want to expose something like that. The whole point of this is to just show you that the optimal integer solution does not have to be anywhere near the optimal real solution.
I was just wondering if it's possible to even see that this is really occurring. Right? Like
in a real world setting?
Yeah.
Well, one thing you can do is you can run the problem with several different values of the parameters. And then you can see what happens to your solution space. And you can see, is your solution stable under small changes in the value of the knapsack? And what might be the case is, if your knapsack is sufficiently large relative to these quantities, you might essentially be in a region where it looks continuous. And that the integer optimal might be fairly close to the real optimal.
So what you meant is go a little bit beyond our constraints and see what happens. Is that what you meant?
One thing is you could then have the size of the knapsack a variable and then just see what happens to your answer as you vary that.
Okay.
And then that would tell you that maybe it's worth doing this research and development to get the super knapsack. And then you would actually maybe even get a sense of how much of an improvement in the knapsack do you need. And you might get a sense, if I can only increase the knapsack by 1 kilogram, it's not worth it. In fact, any increase by less than 2 kilograms is worthless to me. And then trying to figure out exactly how much things are worth. But if you can increase the knapsack capacity by 2 kilograms, how much is that worth?
Increasing it by 1 kilogram is worthwhile, so you can get one of each.
Oh, sorry, okay, you're right. I could then do 1 of each. I'm sorry. So if I can increase it by half a kilogram, thank you, it's no benefit to me. As soon as I get a 1 kilogram increase, it's worth much. So how much does a 1 kilogram increase give me? $50. So how much are you willing to pay for a 1 kilogram increase?
50 minus delta.
Or you'd be at least indifferent to $50. Definitely you would do it at $48, $49, right? How much would you pay for a half kilogram increase? Nothing. It's worth nothing to you. So this leads into the fascinating theory of evaluating options. How much is something worth to you? But the whole point here is that integer maxima and real maxima, they could be very different configurations. If people want, I'm happy to give a lecture tomorrow, which is Wednesday, on when integer maxima for some problems are close to real maxima. This is a Calc 3 problem, Calc 1 problem. I'll pass this out in the daily announcements and just let me know if you want to see something like that. Along these lines, since we have 1 minute left, I don't want to get into a new unit. I'm going to just give you the following question. So you have a company, and there are two people who own shares of the company. And there's some different configurations. One person owns 50%, another person owns 50%. And let's say the company is worth $1 million. How much are those 50 shares worth? I'm sorry? How much are those 50 shares worth? That 50% worth? I'm sorry? $500,000. Now imagine person 1 owns 51% and person 2 owns 49%. How much is that 51% worth? Yes, you control the board. How much is that 51% worth? $1 million. You can make people feel good. I'll give you some shares. You'll be a member of the company. At a meeting of the board of directors, we decided to do whatever the hell I want. And I'm sorry, but your opinion will not be advanced. Let's do another case now. Now there are 3 people. 49%, 48%, and 3%. How much is the 49% worth? It depends. I would say the best answer is $333,000. I mean, you have a little bit more flexibility if you die here and you want to split things up. You can split things up and have sizable blocks. But in terms of voting and in terms of controlling the board, this is still equivalent to this. Any 2 of the 3 dominate. So this is very similar to going back to the knapsack problem in trying to figure out, if I have constraints like this, what do I do about them? How do I choose my investments? And the choice is going to depend on what you're able to get back from it. And so here we saw for $50, we're indifferent to increasing the bag by 1 kilogram. For $40, we definitely do it. For $55, we wouldn't do it. Now there's a big issue we haven't taken into account here, is the geometric configuration of the objects. Just because the knapsack can take 100 kilograms, it doesn't necessarily mean I can take 2 copies of unit 2. And so for something like this, the geometry of the different shapes could matter. If you think about chemical reactions, the geometry has a huge impact on which reactions can go forward. And so in a lot of these problems, it's not enough to just know that you have 100 kilograms. You have to add additional constraints to take into account the geometry of the problem. All right, so this is a good place to stop. If you are interested in seeing a basically review of Calc 1 in 1 day, which culminates in why sometimes integer maxima are close to real maxima, I'm happy to do that on Wednesday. If not, we will probably get into multi-objective linear programming. We may actually have time to do both.